Hey, good morning, everyone. All right, let's go ahead and get started here. So I wanted to open with this question, kind of a little bit of a teaser for everyone. Why do we still use lead-acid batteries today in cars? That's one factor. Rapid discharge, C-rate, exactly, right? It'd be recycling. Okay, that's probably true as well. But the one I had in mind was C-rate, right? Lead-acid batteries are really, really good at giving a lot of current in a very short period of time. Compare that to lithium today, it's not as good at it. That's why you don't see lithium batteries replacing lead-acid batteries in cars, right? So that's the premise of this presentation here, right? How do we find the right use cases for long duration technologies? So 3 main steps, right? If we think about the lead acid example, the reason we could say that is because we know lead acid batteries. We know how they perform. We also know, a good deal about lithium batteries, and we know how they perform. So the first step is accurate modeling. We need to accurately model all the technologies we consider for our projects, including new long-duration energy storage technologies. And then finding use cases in which lithium becomes expensive. Now, this is all from the perspective of trying to find good use cases for new long-duration technologies. So that second step there is geared towards, all right, lithium is the benchmark for, like it or not, it is the benchmark today for grid energy storage, right? So we need to find a use case in which it simply doesn't perform as well. And then third, benchmarking the long duration energy storage technology with lithium in the use cases where lithium isn't as good. All right, so step 1, battery modeling. The way we can achieve that, very straightforward, gathering data either from the OEM themselves, which, is probably the fastest way because, as many of you know, accelerated degradation tests take some time, and in almost all cases, the battery OEMs will perform accelerated degradation testing before third-party testing laboratories. But getting data, either from the OEM or testing labs, creating models using that data, very accurate models that capture all the details, voltage, internal resistance, self-discharge, efficiency, degradation, and then kind of validating that model. And here I wanted to mention some examples of kind of the level of detail that is needed in modeling in order to be able to perform accurate comparisons between technologies. So for example, cell resistance, more than often, if you ever looked at a battery data sheet, you'll just see one number for internal resistance, if any. Most of them don't have that value, but it'll just be one number. But really, truthfully, internal resistance, if you're kind of going to use an equivalent circuit model to model cells, internal resistance varies based on state of charge, it varies based on temperature, so that has to be taken into account in any accurate modeling. Also, self-discharge resistance and self-discharge losses. So for a lot of zinc technologies and nickel hydrogen technologies, self-discharge heavily depends on the state of charge you're at. It heavily depends on the ambient temperature, which is really, really important for technologies that are not temperature regulated. So they're kind of exposed to the ambient temperature. So these are the type of things that we kind of take into account when developing models for lithium and for new long duration technologies. So next here, this one's also particularly important for lithium systems because they're temperature regulated, so which means they're going to have an HVAC system attached to them performing for the entirety of the life of the project. So it becomes important to model how much load that's going to end up consuming if you want to account for the running cost of the project. In other words, the amount of energy lost over the life of the project. Also depends on the instantaneous C rate that you're running at. So the higher the C rate you're running at, the more heat gets dissipated from the cells, the more cooling that requires, the more kind of you're spending on energy, right? Also depends on the type of enclosure. So are you using a liquid-cooled enclosure or are you using an air-cooled enclosure? Both have very different efficiencies. And also the material of the enclosures. We see a lot of concrete enclosures, which are much better at keeping the temperature and isolation versus kind of steel enclosures. So all of that has to be taken into account if we want to perform accurate modeling to draw any kind of conclusions we can rely on. Now this is kind of a sample of validation. So last part I was talking about kind of the losses, the real-time losses modeling, but here this is kind of a different or another kind of aspect, which is degradation. Very, very important for lithium. A lot of factors affect lithium degradation. Cycle life, calendar life, depth of discharge, average state of charge, temperature, C rate. So all of that needs to be taken into account and the model validated. Now, I also want to talk about this part. If you use lithium systems, if you're in kind of the industry, you know that realistically there's a limit on the amount of data you can get for a technology. Accelerated degradation tests, like I said, they take time. So you're not always going to have access to all the data that is needed to accurately model that one cell, that specific model, right? So there has to be compromises. So our approach to these compromises is really full transparency, right? There are instances where, let's just say you're testing model A of a CATL battery, but you don't have kind of, let's just say you don't have data for state of health less than kind of 60%, right? So our approach is kind of fully disclose that along with the model validation report, but also leveraging similar cells of the same cell composition, same LFP, and the same ratio of lithium iron phosphate. All right, so that's step one, the modeling part. Okay, so now that we have that out of the way, let's assume at this point we have accurate models that we can trust for lithium technology, and we have an accurate model that we can trust for a new long duration technology, right? So here we're trying to find the use case in which lithium becomes expensive. So we're going to set some kind of project assumptions. Let's just say, power requirement 100 megawatts at the point of interconnect, duration 4 hours. So that's 400 megawatt hours dischargeable at the point of interconnect, and let's assume a 20-year project life. Okay, and we'll do 2 simulations, right? And this is just focusing on lithium. We're not talking about any long duration technology till now. Okay, so we'll assume 2 cases: one deep discharges, the other shallow discharges. Both of them 1 equivalent cycle per day. All right. So we kind of run the simulation. We make sure that we're meeting the project requirement by being able to achieve the power and energy requirement at different points on the project. At the POI, inverter, battery terminals for both charging and discharging. And then we see kind of how much overbuild this, I'm just focusing on one factor here to start with, which is the most impactful factor, the overbuild required to allow that project to last for 20 years, okay? So in the deep discharge case, we found that to maintain 400 megawatt hours at the point of interconnect for project life, we need to start with 712 megawatt hours at year 0. versus for shallow discharges, we needed just 548 megawatt hours, right? So that's a huge difference. So what do we learn from here, right? What we can learn is deep discharges are not that favorable to lithium. If we can just make, well, I'm not going to say lithium, but for this cell of lithium, right? So we'll make that kind of general assumption here, which brings us to step 3, right? Of course, there's, I want to say there's other factors, deep discharges is one of them, but, high number of deep discharges is another. So there's other factors, but just for the purpose of illustrating the approach here, we'll just focus on this one. All right, step 3, benchmarking long duration energy storage where lithium lags. So here, now we're going to kind of shift to making the use case constant and then trying out different models, one using lithium, the other using a long duration energy storage technology. So we're going to assume 2.1 cycles a day, 2 cycles that are deep discharges, 0.1. We assumed that we were going to perform some frequency regulation at the end of the day. Arbitrary, no kind of reason behind that. And also, the long duration energy storage technology we were benchmarking here, it was Enervenue's nickel hydrogen battery, which we also developed a very accurate model for. And we knew kind of it, from that model that it really liked to be cycling. It has a 30,000 cycle life. It can last for 30 years. We also knew that it was high on self-discharge. Not very high, but relatively high, and had a big dependency on the self-discharge rate depended a lot on the average state of charge you're at on a daily basis and also on temperature. So that had kind of obviously some input into how we kind of specified the use case and specifically the usage profile or the dispatch profile. So here, like I said, we assumed 2.1 cycles a day. We applied that to both the lithium model and to the Enervenue nickel hydrogen model. And these are the results, right? We found that for the Enervenue case, the beginning of life capacity only needed to be 450 megawatt hours compared to 861 megawatt hours for lithium, right? You needed an overbuild factor of 2, basically, for the lithium system. So, at the end, that created an IRR of 5.8% for the Enervenue case, 2.5% for the LFP case for 2.1 cycles. But, and also take into account in the numbers you've just seen is, the other side, right? We talked about degradation, how Enervenue was advantageous because it degraded much less, it had much higher cycle count. But on the flip side, its round-trip efficiency isn't as good as lithium. So in the simulation, we kind of deduced the energy losses over project life. So that's why you see kind of that big part, that green bar there, which is the net present value of the cost of energy over the 20-year project life. And also the cost per, I don't know if it's mentioned here or not. The cost per kWh of installed capacity for the Enervenue case, and this is all public, was $375 per kWh versus lithium at that time it was $280 per kWh. So lithium was actually, at that time much cheaper, and it still today is much cheaper. But even with that, because of so much less degradation, you didn't need to procure as much of it, which at the end resulted in a much lesser cost for the DC block in the Enervenue case. All right. So, conclusion here. The best usage profile obviously heavily affects battery degradation and losses, and accordingly project sizing. And this is not something that should be taken lightly. It does make a big difference exactly how you intend to dispatch a system. Two, all cycles are not created equal. We've seen kind of the impact of deep discharges on lithium systems versus shallow discharges, so that definitely has to be taken into account. We see a lot of, a lot of people kind of doing linear regression with cycles to predict degradation. That is catastrophically inaccurate. And then third, there is no such thing as a best battery. There's a best suited battery for each use case. So, with a methodology like this, we're hoping kind of, the industry can move from, the current way which is a lot of developers apply, which is, all right, what's the cheapest battery we can get our hands on a dollar per kWh basis, and let's just use that everywhere, right? To kind of a approach where, okay, let's use the battery that is best suited for each use case here, which would result in the least overall levelized cost of ownership and levelized cost of storage.